Bismillahirrahmanirrahim, and Assalamualaikum warahmatullahi wabarakatuh, and very good morning to everybody. And we continue our discussions or learning process for chapter 5, which is equally important, okay, because we love to ask students about these stereochemistry topics, because the difficulties of these topics have been highlighted here. So for today, we will study a few things about the stereochemistry, which is quite important in organic chemistry. So you will learn how to determine the R and S configurations. There is the first one. Okay, the second one is enantiomer diastereomers. Okay, and how to differentiate whether the compound have a chiral or achiral compounds. Okay, how to determine the Stereogenic Centers. So stereochemistry is referred as a three-dimensional. It's 3D structure of the molecules. Okay, so representations of 3D of molecules. Okay, that's why it's better if you have ball and stick models, so you can see whether which bond is at the front and which bond at the back. Okay. So as a consequence of stereochemistry, apparently minor difference in 3D structures can be result in vastly different properties. It will give different properties, especially if you're playing around with the drugs. Okay, and different 3D orientations of the drugs will give difference. Some of the drugs will give you the good effects, some not. Okay, instead of treating, it can be a poisons. Okay, so we can observe this by considering starch and cellulose as example, which are both composed at the same repeating units. Okay, so in cellulose, the atom join two rings using equatorials. We already covered last week about the chair conformers. Okay, equatorial bonds. Okay, in cellulose, equatorial bonds. And starch, the oxygen atom, two ring joined by using one equatorials and one axial bonds. Okay, it will give you different properties. And this two difference, okay, in stereochemistry, humans can metabolize starch for energy but cannot digest cellulose. Okay, so with cellulose we are using in material chemistry using that. Okay, so this is 3D orientations of starch and also cellulose. Okay, and constitutional isomers, we already learned about alkenes, about constitutional isomers, chapter 1 also. Okay, isomers. Isomers are different compounds with the same molecular formulas. Okay, so there are two major classes of isomers. Okay, there are a lot of types of isomers, but this is the two major class of isomers. Is the first one is constitutional isomers, and the second one is stereoisomers. Okay, you can easily make a mind mapping to understand more about this one. It's better to do mind mapping. Okay, because I'm doing the technique when I'm a student. Okay, because it's quite hard to understand, but by using mind mappings, it will help you a lot. Okay, so constitutional isomers, or we can do structural isomers. Okay, have a different IP names. There's the first properties, same different functional groups, different physical properties, and different chemicals properties. Okay, so for the stereoisomers, differ only the way atoms are oriented in space. Okay, this is what they call stereo. Okay, in space. Okay, so have identical IUPAC names. Okay, I set prefix in the front. Okay, whether it's like trans or cis, chapter 4, for examples. Okay, you will learn these isomers things when you study chapter 8, 9, 10, no, 9 to 11. Okay, always have same functional groups. Okay, differ in configurations in terms of 3D orientations. Okay, so for constitutional isomers and stereoisomers, this kind of an examples. Okay, so for example, this one is the 2 methylpentanes. They have six H14s, and there is another compound 3 methylpentanes, similar molecular formula, C6H14s, but they have a different names. Okay, so this one we call constitutional isomers. And meanwhile, another example here, like chapter 4. Okay, this one we have cis 1,2-dimethylcyclopentanes. This is cis, okay, stereo, okay, and this one is trans. Okay, and the same molecular formula, but same name except the prefix, the front names. Okay, is a stereoisomers. This one is constitutional isomers. So, non-superimposed mirror image, although everything has a mirror image may superimpose. Okay. So, to superimpose means to align all parts of 2 objects. Okay. And some molecules are like hands, left and right, are mirror image. Okay, like this. Okay, mirror image I've shown in an example here. But they are not identicals because we cannot superimpose this hand. Okay, so molecules or objects that is not superimposed or on its mirror image, we can say this is the chiral. Okay, so superimposables chiral objects, other molecules like socks, 2 socks from a pair of mirror image that are superimposables. Okay, a socks and its mirror image are identical. So, okay, a molecular or object that is superimposables on its mirror image, we can say achiral. Okay. Okay, achiral molecules. Okay, we can now consider several molecules to determine whether they are achirals. Okay. So, for example, water, they have this, okay, this is oxygens, we have H. Okay, and again, with the mirror image, okay, we can easily align this one. Okay, so this one we call a achiral. Okay, meanwhile, for CH2BrCls, okay, I think this compound is not exist in real world. Okay, so we have mirror image and we rotate the molecule to align, and this one is a achiral also. Okay, because it can be overlap each other. Okay, so a molecule label A and its mirror image label B are not superimposables. Okay, and no matter how you rotate A and B, all atoms never align. Okay, so that's CH2BrClF. Okay, I think this compound is not exist in real world, but this is kind of an example with that we try to use to make sure everybody understands. So it's a chiral molecules, and A and B are different compounds. Okay, A and B we can name it stereoisomers. Specifically, they are enantiomers. Okay, so carbon atom with 4 different groups is a tetrahedral Stereogenic Centers. Okay, so it's mean this carbon is Stereogenic Centers. Okay. So in general, a molecule with no Stereogenic Centers will be chiral, except for this we consider in section 17.5. This one we're not discussing because it's chapter 17, subchapter 5. We don't discuss. Okay. we will cover until chapter 5 only. Okay. So with one stereogenic center, a molecule will always be chirals. Okay, with one stereogenic center, a molecule always be a chiral molecules. Okay, so with one or two more stereogenic centers, a molecule may or may be not a chiral. This is kind of statement. Okay, we will see more in exercise and also discussions during tutorials with your tutors. Okay. So plane of symmetry. Okay, a plane of symmetry is a mirror plane that cut the molecule into half, so that one half of molecule is reflection to another half. Okay, it's equally important. Okay, so chiral molecule are usually contain a plane of symmetry, but chiral molecule is not. Okay, so for example, CH2 BrCl2. Okay, they have plane of symmetry. It means this side reflecting this side. This is the plane of symmetry, and this one is chiral. Any molecule that have a plane of symmetry, and we can call it chirals. Okay, if they have no no plane of symmetry like this ones, okay, if we cut in the middles, okay, so we don't have this fluorine and this one is hydrogen, is not symmetric. Okay, and this compound we call a chiral. Okay, if the compound have plane of symmetry, we call achirals. Okay, if not, we call chiral compounds. Okay. So summary of chirality, everything has a mirror image. This is point number 1. Okay, point number 1, mirror image. Okay. So the fundamental question whether the molecule and its mirror image are superimposable. There is another issue. Okay, superimpossibles. If not, they are chirals, okay, and not contain a plane of symmetry. It's another issue that you have to consider is plane of symmetry. There are 3 things you have to consider regarding the chiralities. Okay. So in the terms of Stereogenic Centers and chiral molecules are related but distinct. Okay. So a chiral molecule have more, they have one or more stereogenic center. 4. Okay. So for the stereogenic center, to locate the stereogenic center, examine each tetrahedral carbon. Okay, it's always happen in tetrahedrals. Chapter 1. Okay, in the molecules and look at 4 groups. Okay, you know that tetrahedral have 4 different groups. Okay, 4 groups. Okay, and always omit the consider all carbons that cannot be tetrahedral stereogenic center. This includes CH2, CH3 groups. Okay, so any sp or sp2 hybridized carbons. Okay, so so for example, see the example. For example, this one is considered stereogenic centers because they have 4 different substitutions. Okay, they have protons, bromines. This is alkyl with different length of carbons. Okay, this one is CH2, CH3 for this one, and this one they have CH2, CH2, CH3. Okay, if the compound like this, okay, BR, C like this, okay, they doesn't have any have stereogenic center because they have, if we cut, okay, if we arrange this compound to 3D orientations, we can cut into half, and this one can be a this one, okay, plane of symmetry. Okay, and this one is a can be superimposed. Okay, this one is a chirals. Okay, okay. The point is to know the stereogenic centers. They have 4 different substitutions. That's all. Okay, which is 4 different substitutions. Okay. So multiple stereogenic centers, okay, large organic molecules, okay, this is kind of examples, have 2 or 3 or even hundreds of stereogenic centers, okay. So for example, these ones for analgesic drugs, so they have 2 stereogenic centers, one, okay, they have 2 different types of phenyls. Well, another ones have a more with a CH2. Okay, so this is only benzene. This is the phenyls, and they have alkyl groups here with the branch. Amines, tetraamines, and then other substitutions have kind of esters. So for this one, for this compounds, they have 2 stereogenic centers also. Yes, to make it easy for you, you have put protons here, you can put protons here. Okay, this one have 3 stereogenic centers. Okay, you have to put proton to make sure you understand this is a tetrahedrals. Okay, fructose, for example, for simple sugars. Okay. For enantiomers, okay, enantiomers are not superimposable mirror image molecules, not superimposable. Okay, so any molecule have 1 stereogenic center exists as pair of enantiomers. Okay, for example, alanine, which is an amino acids. Okay, this is an enantiomers, and we can easily draw the mirror image like this. Okay. Another example is a 3-bromohexanes. Okay. So for 3-bromohexanes, this is enantiomers. We can put a mirror here. Okay, let's mirror here. Okay, from A we can easily draw the mirror image for which is B. Okay, so that's why we call enantiomers. Okay. So for drawing enantiomers, to draw both enantiomers for the chiral compounds such as 2-butanol, this is 2-butanol for examples, okay, use the typical conversions by depicting a tetrahedrals, okay. So to form the first enantiomer, okay, place 4 groups H, OH, CH3, CH2, CH3 for any bond in the stereogenic center, okay, and after that, draw the mirror image. Okay, first you have to draw your molecules here. Okay, we call A, and put a mirror. Draw the reflections of these compounds. Okay, this is maintained. Okay, you can see H here. Okay. Okay, this one at the back far away, so you can easily draw like this. Okay, we will do more exercise to make sure you understand about this ones. Okay, it's better to do more exercise if you want to read in hope that you understand directly. Okay, it will be a trouble for you. Okay. So, stereogenic center in cyclic molecules. Stereogenic centers may also occur in carbon atoms that are part of the rings. Okay. So, to find the stereogenic center on ring carbon, always draw the ring as flat polygons. Okay, as flat polygons, and look the tetrahedral carbons they are bonded with for difference. Keyword is for different groups. Okay. Okay, for example, methyl cyclopentenes here, we can convert to flat polygons. Okay, this is the flat polygons. Make sure you understand that tetrahedrals have 4. Okay, so you have to put another bond to which is represent protons. Yeah, so this compound is not stereogenic center because they have 2 identical groups. Okay, if I put like this methyl, it will be different. Okay, it's become stereogenic center. Okay. Okay, the second example, 3-methyl-cyclohexanes. Again, convert the compound to flat polygons. Okay, like this. Okay, you have to understand that carbon can make a tetrahedrals. Okay, and after that, put the proton here. And this one, in this case, they have three different functional group. Okay, three different functional group instead of protons. Okay, this is the alkene. Okay, this is another groups, and this is only methyl CH3. Okay, this one we call stereogenic center. Okay, in 3-methyl-cyclohexane, the three CH3 and H substituents that are above and below the plane on the ring can withdraw the wedges and a dash as usual. Okay, so this is, we are going to another stage, how do we try to draw in 2D representations. Okay, so we can represent like this, draw, okay, wedges and dash. Wedges front, at the front, if we imagine in 3D orientations, okay, at the front, okay, meanwhile look for the protons at the back. Okay, this is, if we see the 3D orientations here, we can see this one point up to you. That's why we call at the front. Okay, menuju pada kamu. Okay, so for this carbon, okay, at the back. Okay, tak belakang, menjauhi kamu. Okay, and we put a plane of symmetry here, a mirror. Okay, it's not plane of symmetry, it's mirror. And after that, draw the second structures, which is enantiomers. Okay, by doing the same, but the arrangement is similar also, right? Okay. So some biological active molecule with stereogenic centers, and the ring, this is a few examples. These are thalidomide. Okay. So so this is examples. This is anti-drug for nausea drugs, and the difference is this one. Okay, if we try to draw the enantiomer, is a teratogens. I think teratogen is a poisons. Okay, and we can easily, by changing this functional groups only, we can see the different effects of these both compounds. Okay. So some biological active molecule with stereogenic centers or ring. Okay, for example, this is a sugars. Okay, they have different functional groups here, so we can easily doing the same protocol to convert everything in polygons, flat polygons. For example, this one, okay, have protons, they have different substitutions here. Okay, so this is the stereogenic centers, and this is also stereogenic centers. We have methyl together with OH here. We have another functional group with this side, and they have also hydrogens, including the hydrogens. Okay, so there are lots of chemicals or molecules in the world that have so many stereogenic centers. Okay, so this is a very famous example, peptide cells. Anybody who are on chemo, we are using these drugs. Okay. So labeling stereogenic center with R and S, this is equally important. Okay. Maybe after this, after we finish the lectures, we can I will post a few examples, and maybe you can start to do it, and maybe on Thursday we will start to discuss. I will choose a few questions and we start to discuss. For the rest, maybe you can discuss with your tutors, because I get a few information from your tutors. Some of the groups already will be finished soon to discuss tutorial 1. So I think it's better to use this time, okay, to add more questions and discuss with your supervisors, your tutors. It's better to do that, okay? Since enantiomer are two different compounds, okay, they need to be distinguished by name, okay? So this is done by adding the prefix R and S, okay? That's why we call stereo, okay? Stereo, it's mean the positions, okay? Everything name is the same, but the orientation or representation of the compound could be different, okay? So the rules number 1, to designate enantiomer as R and S, okay, priorities must be assigned to each group bonded to the stereogenic center. First, you have to determine whether that particular functional groups or the carbons or anything, okay, in this case, in carbons, have different 4 substitutions. If they have 4 different substitutions, that carbon is the stereogenic center. This is the first rule. It's not the first rule, this one, okay? So you have to make sure this which one is which carbon or which atom have a stereogenic centers, okay? So, and second one, you have to assign each group bonded to the stereogenic center in order decreasing atomic numbers. So you have to remember atomic numbers. Okay, not much, right? Not much. So for the first one, for example, okay, the atom high priority numbers get the highest priority. The atom highest atomic numbers, we get the first priority. In this case, we have 4. Okay, this is a stereogenic centers. Why we call stereogenic centers? Because it's attached with the 4 different substitutions. So it's the first one. The second one, you have to arrange all the substitution by increasing atomic numbers, and the highest atomic numbers we get the highest priority, which is number 1 in this case. Okay, so between okay, of course, proton, the size is quite small. Okay, so it's become the lowest priority numbers, get the lowest priority numbers. Between bromine, fluorine, and chlorines, bromine will be number 1. Okay, chlorine will be number 2. And fluorine will be number 3. If I change fluorine with iodine, this will be different. Iodine become number 1. Okay, if I change fluorine with iodine, iodine become number 1, bromine become number 2, chlorine will become number 3, and fluorine become number 4. Okay. So rule number 2, in a 2 atom on the stereogenic center are same priority based on the atomic number of the atom bonded to these atoms. Okay. For examples, okay, wait. Okay. One atom of higher atomic number determine the high priorities. Okay. For example, this one. Okay. So you know proton will be number 4. Okay. No number 5. Jangan pandai-pandai buat number 5. Only 4. The highest number, the lowest number is 4 only. Okay. So, okay, between oxygens and they have carbon here. They have carbon here also. So oxygen will be number 1. Okay. So siapa nak ambil nombor? Who want to be a number 2 or number 3? Okay. So for the second rules, okay, carbon will bonding with hydrogens. And this one will bonding with carbon, okay, hydrogens. So this one is number 2. That's why they have 1 carbon, 2 hydrogens. Okay, this one is 3 hydrogen only. So this one is number 2, and this one is number 3. Okay, doing more practice. Okay, doing more practice. If you want to understand during the lectures, it's almost impossible. Open your books. Okay. So rules number 3, in 2 isotopes are bonded in stereogenic center, assign priority order decreasing mass numbers. Okay. So thus it's comparing 3 isotopes of hydrogens in order properties is, okay. So for example, in hydrogens, we have 3 isotopes normally. One is protons, another one is deuterium, okay, and you have to, it's quite what I can say is we don't playing with too much with the isotope. I cannot say this is quite important, okay. So rules number 2, to assign the priority of atoms, there is part of the multiple bonds, okay, double bond for examples, okay. Treat the multiple bonds atom equivalent the number of single bond atoms, okay. So for example, C double bond O, which is referred as a carbonyl functional groups, okay, considered to be bonded to the 2 atom oxygens, okay. So this one, okay, for this one, okay, we talk about its equivalence to carbons bonded to oxygens, okay, carbon bonded to the oxygens and carbons, okay, and assign the priority. Okay, assign the another common multiple bond are drawn below. For example, this is carbonyls. So this is the carbonyls, the carbonyls, and this is another examples for the double bonds. Okay, alkenes and alkynes. Okay, so equivalent to carbon bonded to the carbons. Okay, carbons. Okay, this carbon. See the color. Okay, bonded to another carbon, similar carbons. Okay, so each carbon, the double bond is drawn as twice. Okay, so for triple bond is shown here. So it's equivalent shown here. It means if the molecules have a similar double bond, single bond, so double bond will be highest priorities compared to the single bond. Assign the priority of stereogenic centers. Okay, so the bonding stereogenic centers are bonded to bromine, chlorine. Okay, so this stereogenic center is not bonded directly to iodines. Okay, this one's number 1. Okay, even though you see this is the iodine, so you have to see the stereogenic center bonded directly to whom? Okay, in this case, then we have bromine, proton, chlorine, and carbon, not iodine. Okay, that's why the priority is number 1, number 2, and number 3. Okay, so for this second example here, okay, almost all the alkenes, okay, single bonds, okay. So, but you have to see the priority number of the bondings. Okay, so for this one, they are bonding to the carbon. Okay, the longest one. This is the longest change. Okay, and so this one is bonded to the carbon, proton. Okay, this one is bonded to carbon. Okay, carbon is also. Okay, this one is only proton. This one only carbon and carbon and carbon. Okay, so get the this branch get the highest priority because carbon is bonded to another 2 carbons. Okay, these 2 carbons. Okay, this one, that's why it's the first highest priority. Okay, and the second one here, okay, they have bonded with another carbon and protons, but they have a lone change here. This one. Compared to this one. If the length between 3 and 2 is similar, it means this one not a stereogenic center. Okay, because we have to understand stereogenic center, have to going back to the original definitions. There are 4 different substitutions. Okay. So in this case, OH get the highest priority because OH has higher atomic numbers. Okay, C double bond O2 CO2H. Okay, they have 3 bond on oxygens. Okay, and get the highest priority than CH2OH. Okay, because this one is carbon. Okay, this one is oxygens, protons, carbons. Okay. Okay, of course, this one get a number 1 because it's find oxygen first. And compared to 2 and 3, this one, CH2OH dengan carboxylic acid is become highest priority compared to this one. Okay, going back to the previous slide. And lastly, of course, the proton will be the lowest priority numbers. Okay, how to assign R and S? Okay, so label the enantiomer R and S. For example, they have 2 enantiomers of 2 butanols, butane to all, 2 butanols is okay also. So priority numbers of 4 groups, we have it here. So first OH, okay. This one, of course, number 4. Okay, we have CH3, CH2. This one become number 2. This one become number 3. Okay, in this case, 1, 3, 2, 4. Okay. Okay, you can refer page 186. So let's start number 2. Okay, for each enantiomers, I oriented the molecule the lowest priority number 4 at the back. In this case, okay, on the dash wedges, clearly here. Okay, I see this one is back, right? This one is front. And visualize the relative positions, the remaining 3 groups, priorities, okay. We ignore this one, okay, because we already put that one is at the back, okay. So for enantiomers to butane to all, look forward the priorities group and draw behind the plane, draw the CH bonds. We can put it like this, okay, and similar to the enantiomers B's, okay, and it will present different arrangements. This one is the Y's, this one is the, okay. So trace the circle from priority groups 1, 2, and 3. Okay, this is very important info. Clockwise are, okay, and counterclockwise or anti-clockwise as isomers. Okay, so for this one, okay, for this one we have 1, 2, and 3. Is these directions. So clockwise is become R isomers. Okay, and from this one, these circles, these directions, we call S enantiomers, R and S enantiomers. And after that, we can put the stereoisomers representations, whether it's R, or this one is R, butane to all, and this one is S, butane to all. Okay. Okay, orienting the lowest priority group at the backs. Okay, if the lowest priority group is not facing toward back, rotate the molecule 120 around the stationary bond axis. Okay, we have to rotate and flip 180 degrees. Okay. So, and after that, we can get the correct answers. Okay. The easiest way is to put this, the lowest priorities at the back. Okay. If the lowest priority at the front, okay, if you get the compounds, okay, if the lowest priority at the front, okay, if you get you assign the orientation first, and after that you reverse the answers. If the compound FR, the answer is S. If S, the answer is R. And we will do more exercises. So don't worry. Okay? Jangan cemas, okay? So you do that one. Okay. So for the diastereomers, the molecule with n Stereogenic center, n become any numbers, okay, 2 power of n, okay, actually 2 power of n, yes, can become any numbers, okay, cannot zeros, okay. So the maximum number of stereogenic stereoisomer is 2 power of n. Okay, this one is okay. So when n, if they have 2 stereogenic centers, 2 power of 2 is become 4. Okay. Okay, with 2 stereogenic centers, there are 4 stereoisomers can be drawn. Okay, and although some of them may be the same molecules, you draw 4 stereoisomers, but you have to cross-check whether they're the same molecules or not. So we will do exercise about this one. Don't worry. Okay. So some of stereoisomers will not be a mirror image of each another's. Okay, diastereomers are not mirror image of stereoisomers. Okay, so finding the possible stereo. Okay, let us consider stepwise procedure to finding all the possible stereoisomers for 2,3-dibromopentenes. Okay, so for examples, we have this kind of compounds. Okay, the 2,3-dibromopentenes. Okay, this is the skeletal structures, and we put also, we know that they have a two Stereogenic centers, Stereogenic centers 2, 1 and 2 here. So we put a mirror, and we reflect the structures. Okay, if you know anybody who study physics, I guess. Okay, for the mirror, it's just a consistency. Okay, left become right, right become left. Okay, for example, this one is close, this part is close to the mirror, so it's become like this. Okay, this one is at a far away. Okay, so after drawing the compounds of the mirror image, place B, okay, which is the second one, second structures. Okay, place B. B directly to the top and rotate 180 is become like this. Okay, the difference is you can see the difference. Okay, rotate 100 B to 100 degrees and place on the top of A to see the top alignment. You can see here the difference is this functioning groups. Okay, okay. So and after that. Okay, hydrogens, if we rotate 180 is become, and from the back is become, move to the front. Okay, and this one for the bromines from the front, we move at the back. Okay, it's become like this. Okay, and we try to align this one. We can conclude that A and B are different molecules. Okay. So in this case, atom A and B does not align, making A and B not superimposed, and we call this enantiomer. Okay, we will do more exercise. Don't worry, don't worry, don't worry. So A and B are 2 of the 4 possible stereoisomers of 2,3-dibromopentane. It means we already drawn 2. They have another 2. Okay. So switch the position of H and bromines of any 2 groups. Okay, in this case, they decide to change these positions. Okay, just change directly. Okay, bromine become at the front, bromines become at the back, protons become at the front. And switch the positions, and we declare this compound as C. Okay, draw the mirror and reflect the structures. Okay, and we put is D. Okay, so and after that we have 4 already. Okay, 4 already, 4 enantiomers. Okay, so we can do some conclusions. Okay, A and C are diastereomers. A and C, we can see A and C. Okay, A and C are diastereomers. Okay, A and C are diastereomers. Okay, this last one. Okay, A and B are enantiomers. Okay, C and D are enantiomers. Okay. Okay, B and C are diastereomers. B and C are diastereomers. Okay, I will show you how. Okay. And B and D are diastereomers. Okay. So for enantiomers, okay, the terms of enantiomers in this case is A and B are enantiomers. Okay. Now we will do more exercise to make sure that you understand. It's better to do that. For the diastereomers, it's only different in this carbon only one carbon difference. That's why we call diastereomers. If there are more carbon difference, we call enantiomers. Okay, diastereomers, one carbon is same. This one is same. Okay, this one is difference. Okay, if we say about A and C. So let's say B and D, okay, for examples, but B and D, you have to rotate the structures, so you cannot see. Okay, let's say for the B and D, what is difference? Okay, the B and D is diastereomers. It's only different, only one carbon, okay, in this case. Okay, why? Because this one is similar. This one is different. Okay, to determine between A and C, it's okay. To determine between B and C is a little bit difficult because you have to rotate the structures. Okay. So for the stereoisomers of 2,3-dibromobutanes, okay, find the stereoisomers of 2,3-dibromobutanes. Okay, since the molecule have two stereogenic centers, okay, we have here 1 and 2, 2 power of n, 2 power of 2, 4. Okay, so to find all stereoisomers of 2,3-dibromobutane, that is the first example. This is the second example. Okay, once you have to draw the stereoisomer A for this 2,3-dibromobutane first, and put the mirror here, and do some refractions. Okay, so you can get the B. Okay, and after that, doing the same thing, change this carbon or these carbons, change the positions between bromine and protons. Okay, so you will get the second structures, C, and after that, put the mirror, draw the reflection structures. Okay, and you will get D. Okay, if you see clearly, D, okay, and C are identicals. Okay. So this is the step 1 by steps. Okay, about how to draw the stereoisomer of 2,3-dibromobutanes. Okay, so compound C contain plane of symmetry. If you see C and D, okay, plane of symmetry is a achiral. Okay, a meso compound of achiral compound can contain tetrahedral Stereogenic center. Meso compounds, okay, as achiral compounds that contain tetrahedral Stereogenic centers. C is a meso compound. If you see clearly, okay, plane of symmetry, we can see the reflections between others. Okay. So meso compound generally contain the plane of symmetry. Okay, any compound have the plane of symmetry when you try to draw the enantiomers, a set of enantiomers. Okay, there is a meso compounds. Okay, that's why what I said before, draw all the possible enantiomers, okay, as stereoisomers, okay, and after that you have to determine which one is enantiomers, which one is diastereomers, okay. Because one stereoisomers of 2,3-dibromobutane isoperimppossible is a mirror image, there are only 3, okay. In previously we know there's a 2 power of n, right? In this case they have 2 power of 2 become 4. We in theory, okay, we propose this compound have 4, okay, 4 stereoisomers, okay, but you have to check, okay, among the stereoisomers. In this case they have only 1 meso compound. Instead of 3 it's become instead of 4 it's become only 3. Okay. Yeah. Okay, this is kind of conclusions for this 2,3-dibromobutanes. Okay, A and B is enantiomers. Okay, a pair of diastereomers A and C. Okay, B and C. Okay, we will do more exercise. Don't worry. And okay, I think that's all for today. We will continue on next Wednesday. For today, we already covered about how to determine the achiral or chirals. Okay, we already discussed about the plane of symmetry, which is quite important to understand about these ones. And we have to arrange the chirals. Once you know the compound have a chiral center, you have to arrange based on priority. This is another one, the things that we already studied. And the last ones, we already learned how to determine R and S configurations, clockwise and anti-clockwise, okay? And we have studied also about the how to determine the compound which is contains stereogenic center, how many stereoisomers they have, 2 power of n, okay? N is number of stereogenic centers, and at the same time you have to check, cross-check the answers or the structures that have you drawn, whether they are enantiomers, diastereomers, or meso compounds. Okay, I think that's all for today. It's quite heavy for these subjects, but we are doing slowly this one. Okay, I think that's all for today. Thank you very much. So anybody want to meet me tomorrow? I'm sorry, I have a full day meeting or workshops with Mosti, so I'm not be here. Okay, I hope everybody are okay with chapter number 1 and chapter 4. Currently we are studying, but for today we are covered chapter number 5. I will choose a few questions from the books. It's easy for us to discuss, so hopefully we can do it together on Thursday. And be friends with this book, okay? There has a lot of information that you can gain from here. Okay, it's okay if you have a soft copy for the books. At least there is information. Okay, if you depend 100% from the lectures I given, it's almost impossible to do that. Okay, and for the quiz, I'm quite surprised. There is, I think, if a lot of students get full correct, it's good. I'm happy for that. It means the question is quite easy for you. So thank you very much. Stay safe, stay healthy, and we will see you on Wednesday, inshallah. Okay, bye-bye.
Yes, come on, shorty, let's go. Girl, I see you over there in the corner of the dance floor, and I know you're acting shy, looking at the corner of your eye. So I pick my heart up off the floor, move my feet closer to yours, catch my breath and I say, I'm the one you're looking for. So come on, dance a little dance. Take my hand, darling, take a chance. You be my queen, I'll be your king. Show you everything that you've been missing, shorty. So come on, dance a little dance. Got me in a trance in just one glance, so don't wait no more. I'm the amor, I'm the one Oh, girl, I see you over there hesitating, deliberating. You keep me waiting on a sign, looking at the corner of your eye. So I pick my feet up off the floor, move my hips closer to yours, catch my breath and I say, I'm the one you're looking for. So come on, dance a little dance. Take my hand, darling, take a chance. You be my queen, I'll be your king. Show you everything that you've been missing, shorty. So come on, dance a little dance. Got me in a trance in just one glance. So don't wait no more, I'm me, I'm more. I'm the one you're looking for, shorty. I'll be the one you're looking for, shorty. So come on the dance floor and baby show me all your moves, all your grooves. Shorty, I got something to prove to you. So come on, take a little chance. Got me in a trance in just one glance. So don't wait no more, I'm me, I'm more. I'm the one you're looking for, shorty. So come on, dance a little dance, dance a little dance. Come on, dance a little dance. So come on, dance a little dance. Take my hand, darling, take a chance. You be my queen, I'll be your king. Show you everything that you've been missing, shorty. So come on, dance a little dance. Got me in a trance in just one glance. So